Today, we need to learn about forces and net force. Now, we've already done a little bit with forces, right? When we talked about free fall, I told you that an object is in free fall if the only force on it is gravity. And when we did vectors, you guys did problems where there were forces and you added the forces together, using vector addition. So this is just going to kind of begin what you learned so far. There's a terrible use of that word. All right, so here we go. Some definitions. Force. All right. Symbol for force is a capital letter F. All right. The definition of a force is a push or a pull on an object. A push or a pull on an object. All right. Now, when you measure force, you're literally measuring how hard the object is being pushed. All right. If you've ever lifted weights, you know that the heavier something is, the harder you got to push to lift it, right? Or pull to lift it. Right? Because you're using more force to lift things that are heavy. All right. So it turns out that you can measure force in either pounds or newtons. Bless you.
Bless you.
You all know what a pound is. A pound is basically the force required to lift a 1 pound object. If you're lifting 50 pounds, you're exerting about 50 pounds of force. Okay? Now, pounds, unfortunately, is not metric, so we are going to use newtons to measure force. So, what is a newton? Well, approximately, this is not exact, but 5 newtons is very wiggly equal sign. 5 newtons is about equal to 1 pound. All right? So if you weigh 100 pounds, that's the same as about 500 newtons-ish. Okay? Now, that is just enough for you to do sort of a mental conversion if you're trying to decide if your answer makes sense or not. All right. We will learn a more formal conversion after we talk about mass and weight and how those things interplay with each other. All right. So to further help you kind of understand what a newton is, I'm going to show you what a newton is. So to measure force, you use what's called a scale. Right. If I want to find out how much force is needed to hold me up, I stand on a scale. Right. All right, and the scale, technically speaking, the scale does not measure how much you weigh. It measures how hard the scale is pushing to hold you up. Okay? So anyway, it's measuring how much force it's exerting to hold you up, right? So what I'm going to do is I'm going to pass around one of these, well, a few of these. They're called spring scales, all right? And when you pull it, it measures how much force you're exerting, all right? So it's got 2 calibrations on it. One side has kilograms. All right, we will never, ever use the kilogram side because kilograms does not measure force. Whoever manufactured these scales, I would like to punch because kilograms isn't force, it's mass, and we'll learn more about that difference later on, but it's very misleading. So pretend that the kilogram side is not here. It is not our friend. Instead, we will use the other side, which says newtons. All right. So when you get this, what I want you to do is just take a minute to play with it. The first thing you're going to notice is 1 newton of force is a very small amount of force. I mean, it's 1/5 of a pound about, right? So it's a very small amount of force. So what I want you to do is hold the spring scale with one hand and I want you to use your pinky finger and pull and exert 10 newtons of force. Okay, so right now I can feel that I'm pulling this. If I put my finger on the end of the hook, it'll hurt. Ouch. Okay? So I'm not going to do it any harder because I will probably cut myself. All right, but so pull, exert 10 newtons of force. Then pull with 20 newtons of force. And what you'll discover is you got to pull a little bit harder. Okay? So I can tell right now, I can feel that I'm physically exerting more strength with my pinky finger to exert that 20 newtons of force than I was when I was exerting 10 newtons of force. Cool? All right, and then notice it doesn't have to be a pull. Of course, it can be a pull, but it can also be a push. So use your pinky finger and push with 10 newtons, and then push with 20 newtons, and you can tell that it's more force. Cool? Yes, sir?
Is force exponentially bigger? Does it take the same amount of force to go to push 1 newton to 2 newtons as it does from like 25 to 26?
No. No, it's
Like, does it get
You have to add the same amount of force to go from 25 newtons to 26 as to go
yeah,
from
1 Newton is 1 Newton. So if you're going 1 Newton more, then yes, it's a linear relation. All right, so I'm going to put one of these in the front of each row. Take one, pass them back. When you're done, I'll put the box at the back of the room. Make sure you look at the Newton side, not the kilogram side. And you get your very own.
wow?
All right. When they get to the back, just drop them in the basket here. All right. Questions? All right. So we will pretty much always be using newtons in this class because of time. Okay. In the same way that we usually use meters instead of miles or feet, usually. All right. So, examples of forces. There are a ton of different kinds of forces in the world. All right? You do not need to write down everything that's on this slide, but this just sort of describes some of the different types of forces that we'll be talking about throughout the year. As we go through this chapter, we'll learn more about each of these types of forces. All right? So, probably the most common example of force, or at least the one that you're most conscious of in day-to-day life, is the force of gravity. Gravity pulls stuff down, right? That's a force. When I let go of this pen, the reason that it accelerates down towards the Earth is because gravity is pulling it down with a force which we call the force of gravity. All right? When we describe forces, we will always label them with a capital F and then a little subscript to further describe the force. So here, capital F stands for force. What force? G. Oh, gravity. Force of gravity. Okay? We will be learning, so this is lecture 1 of, I don't know, like 7 or 8 lectures this chapter, okay? Lecture 4 will be about the force of gravity, okay? So the first couple chunks of our notes here, we're going to talk about gravity very sparingly, all right? And then we'll learn more about gravity in a few lectures after we get the first 2 laws under our belt. Cool? Questions? Okay, another example of a force is the force of Roy. A person can push something. Right? So here, look, here's the force of Mr. Hecker. Right? Okay, that's going to be super common. We're out very frequently. We're going to have, the force of a person pushing or pulling a thing. Okay, and so I usually just label it F of, and then I'll either write the person's name or just the initial if it's clear. Good?
Yep.
All right. Now this is a weird thing. Stuff can push stuff. All right. Obviously, people can push stuff, but things can push things. All right, my water bottle is sitting right there on the table. Thank you again, Griffin, for filling it up. Gravity is pulling it down, but it's not falling for some reason. Why is my water bottle not falling? Because the table is pushing it up. The table is preventing it from falling, right? So the table right now is physically exerting a force, pushing it upwards, preventing it from falling. Just like if I hold it, now I'm exerting a force preventing it from falling. And if I do this all day, I'm going to get tired, right? Make sense? All right. So, questions on that? Yeah.
So, if you get tired from holding it all day, will the table eventually get tired?
No. So why this happens on a molecular level is the protons of the table are repelling the protons in the water bottle. It's opposite. Or like charges repel. So eventually they get close enough that there is enough repulsion that they can't get any closer. Yes, thank you. Totally would be electrons. My bad. It's been a while since I took chemistry. I know better. I just wasn't thinking. All right. Everybody good? And thank you. You're right. Electrons, not protons. Okay. Everybody good on force of the table? All right. Another common force is the force of friction. All right. This is something we're going to spend a few days on learning about friction. So for now, here's what you need to know about friction. Anytime two objects are either sliding across each other or, say, trying to slide across each other, like right now, the table's sort of trying to slide across the floor, but I'm not pushing hard enough to overcome the friction between the table and the floor, so it's not moving. Okay? So anytime two objects are either sliding across each other or sort of trying, in air quotes, to slide across each other, friction tries to prevent that from happening. Okay? So friction always acts in the opposite direction of the direction the objects are sliding relative to each other, or the attempted direction of slide. Does that make sense? All right, let me say one other thing and then I'll get your question. All right, so where does it come from? Well, again, it goes back to the electrons. On a molecular level, the surface of this floor is not perfectly flat, right? The floor is made of molecules, right? These molecules have little bumps and ridges and stuff, right? So if you imagine taking two pieces of sandpaper and trying to rub them across each other, what happens is the grains of sand from one piece of sandpaper sort of bump against the grains of sand on the other piece of sandpaper, and the grains of sand push each other, right? Right? The same thing is happening with the molecules on a molecular level. The molecules of one atom, or one object, I guess, sort of bump against the molecules of the other, and it results in this friction. Okay? We will learn more about that a little bit later on, but for now I'm going to kind of leave it at that. But on a molecular level, nothing is perfectly smooth, so the two surfaces kind of bump against each other. Cool? So,
Is there like a lost and found classroom? Like, if I lost a lab.
I gotcha. Let's talk after the lecture.
Okay, what?
Yeah. Yes.
Is friction reliant on gravity at all?
Yeah, so friction depends on a few things, and again, we're going to learn about this more later on. It depends on, loosely, sort of the pressure between the two surfaces. Pressure is probably not even the right word there, the force between the two surfaces. But that's sloppy too. We'll learn more about it later on. And then it depends on what's called the coefficient of friction. That is sort of just a ratio that measures how rough or how smooth the surface is. Okay. And then we'll learn too, there's two types of friction, sliding friction and non-sliding friction, static. So, okay. Yes, it depends on the weight contributes to friction because it adds extra pressure between the two surfaces. And you guys can all see this. Look, rub your hands together. Lightly. If you do this for a while, they're going to get warm, right? Now, push them together tighter and rub them together. Right? Not necessarily faster, but just pushing tighter, they get hotter faster, right? If you push harder, right? That's because there's more sort of pressure between them. We'll call it normal force is what we'll call that later on. But okay. So if you want to write something down about force of friction right now, I guess what I would probably write down is this first sentence. Oh, no. Stupid smart board. So if you want to write down one thing about friction, I'd write that down. And then the rest is just sort of my sandpaper example, sandpaper analogy. Good? Any questions? He's also got one up there today. That's that.
It is not my fault.
All right. Are we good?
Yes.
Problems? All right. Okay. All right. Couple important things about forces. So, oh shoot, I thought of a seventh one last hour. Hopefully I'll remember it while we're working through this. Okay, so some of these things are going to be obvious to you, so don't feel like you need to write them all down. But these are things that I see students struggle with, so I just want to get them out right now. Here are some things that you need to know about forces, all right, in no particular order. So first of all, number one, when Roy pushes a box with a force of, say, 5 newtons, that's a measure of how hard he's pushing the box. It has absolutely nothing to do with how fast the box is moving. Very often students will say, oh, a box is moving with a force of 5 newtons. That sort of doesn't make sense, because force doesn't equal motion. Force is just how hard he's pushing the box. All right? I can push this wall with 5 newtons and nothing happens. I can push this desk with 5 newtons and nothing happens. But I can probably push this table with 5 newtons and it'll move. Okay? So there are a lot of things that are going to affect what the object is going to do. There are other forces that are going to affect it. There's the mass of the object. All right? Furthermore, you can have something going, like, theoretically, I could have, well, I'm getting ahead of myself. Okay, are we good? So don't make the mistake of confusing force with velocity. They are not the same thing. Force is just how hard it's being pushed. And how fast it's moving is a completely separate value. Cool? Okay. Secondly, I just commented on this. Remember, you can push something and have it not move, right? Because there could be other forces on it that are preventing it from moving, or that are somehow affecting its motion. All right, and even more important, maybe not more important, but more often confused is number 3. Just because you're pushing something in a certain direction doesn't mean it's moving in that direction. Okay? So imagine somebody forgot to put their car in park, and it just starts rolling backwards. Maybe it's rolling down a gradual incline or something, right? And my baby's on the floor over here, and I'm like, oh no, my baby. But it doesn't occur to me to pick up the baby, so I try to stop the car, right? So cars are heavy, right? They have a lot of mass. They have a lot of what we'll eventually call inertia. All right, so the car's rolling at me at, whatever, 3 miles an hour, and I'm like, oh no, and I get in front of it and push it. When I start pushing it this way, does it immediately start moving that way? No, it's going to be like one of these. It's going to be moving this way, and I'm going to push it forward, trying to stop it so it doesn't squish the baby, right? But I'm slowing down its motion, right? So just because something's moving in a certain direction doesn't mean, let me say it. Just because you're pushing something in a certain direction doesn't mean it has to be moving in that direction. Make sense? Sorry for the grizzly example. All right. Are we all good, though? Everybody?
Yeah.
All right, here's another even more common example. Check it out. After I let go of it, between the time it left my hand and the time it got to the top of its path, point for me. What direction was the water bottle moving? Up, right? But what was the only force on it? Gravity pulling it down. Right? So at that instant, it was moving up, but gravity was pulling it down. That's why it didn't keep moving up forever, right? Because gravity wanted it to stop moving up. Okay? So please don't confuse the direction of the force with the direction of the motion. They're not the same. Cool? All right, number 4. We talked about this last chapter. Force is a vector. So it includes both magnitude and direction. Pushing this table this way with 5 newtons is very different from pushing the table this way with 5 newtons. It's important that gravity pulls stuff down as opposed to up, right? It would suck if gravity pushed stuff up, because then we'd all be in outer space and dead. Sorry, we're in discussion today, I don't know why. But, make sense? All right, cool. Number 5, just like velocity, force can be negative, right? If we're talking one-dimensional motion, me pushing the table to the right with 5 newtons would be positive 5, whereas pushing it to the left with 5 newtons would be negative 5. Cool? All right, finally, number 6. This is huge, and hopefully not super surprising, but probably a new way of thinking about this for you. When we do calculations and when we make our drawings of forces, which is what we're going to spend a lot of time talking about today, when we do calculations and drawings, we're going to treat a push exactly the same as a pull. Right? So in other words, me getting over here and pushing the table this way with 5 newtons is exactly the same as me standing over here and pulling with 5 newtons. Because both times I was exerting a force that way, to the left, right? All right? So, in other words, pushing a box to the right with 5 newtons is exactly the same as pulling it to the right with 5 newtons. All right? So what's going to be important is what direction is the force pushing or pulling, and how much force is there. Whether it's a push or a pull is kind of inconsequential. Good. Anybody have any questions about a few important things about forces? All right, let me see if I can remember what number 7 was. I thought of something last hour, and I said to them, I should have added that to my list of things. If I'd been smart, I would have written it down. Wait for one more second.
Did you say corpse?
Maddie, do you remember?
No.
No. You weren't in my 4th hour class, that's why you don't remember? I don't know. Oh, it'll come up at some point later on in the class. All right, everybody good? Okay. All right, now, we are going to talk a ton today about just making your drawings. Eventually, they're going to be known as free body diagrams. We sort of don't know enough to call them that yet, but that's sort of where we're headed. This is like laying down the foundation work for how you draw a free body diagram. Now, I don't know if you have to write all of these down, because most of them, once you see it once, you'll be like, oh, that makes sense, and you'll just always do it that way. Okay, so don't feel like you have to write all these down. But let me just run through the rules. So what's going to happen is we're going to have an object. All right, and we're going to be interested in a couple things. We're going to be interested in what forces are on the object, and then tell me something about its motion. What's the velocity at the moment we're talking about? What's the acceleration at that moment, etc. Okay? So the big thing to understand here is last chapter we were talking about motion, right? We'd have an object that rolled up a hill and it came back down a hill or whatever, right? And when we did that, our drawing sort of represented multiple moments in time, right? We were, drawing the path that it followed as it went up the hill and came back down the hill. Right? And so you had an initial velocity and a final velocity. Now we're not doing that. When we make these force drawings, what we're doing is we're representing, it's like a snapshot, one moment in time. So you've got this moving object, click, we take a picture of it, and at that moment, what forces are on it. Okay? So to do that, here's what you do. You draw the object. I just draw a box. A lot of people just use a dot, which is technically the right way to do it. But I, for whatever reason, for a first-year physics class, I think there's value in drawing a physical object, like a box or a car or whatever it is that you're doing. Okay? So when you draw your forces, the force arrows are always going to start inside the object and point out. All right? So your arrows are never going to point into the object. Your arrows always point out of the object. Always, without exception. Okay? Sorry?
Yeah.
Whether it's getting pushed or pulled does not matter. The arrows always point out. All right, and I'll illustrate that in a minute. Okay? Obviously, the arrow is going to point in the direction that the object is being pushed or pulled in. The larger the force is, the longer the arrow. This is huge. It's, for whatever reason, students really resist this. You have to label your forces. When we get farther into this chapter, we're going to have as many as like 6 and 7 forces acting on an object at a time. You have to label them. A, because it'll help you keep your stuff straight. B, it'll allow me to know if you know what's really going on. And if you make a mistake, I'll be able to figure out where your mistake was. You know what I mean? So label your force. Finally, this seems like a weird thing to say, but if there's no force, don't draw an arrow. Sometimes I'll give a problem and I'll say, Roy pushes a box across a frictionless surface, and people will draw an arrow and write force of friction equals 0. But if there's no force, then how do you know which way to draw the arrow? Right? And on top of that, remember, the length of the arrow represents how much force there is. Where is it? Larger forces have larger arrows. So no force would be no arrow, right? Okay, so that's the deal with force vectors. Okay, the big thing to remember there is exactly what I was just saying with Fred, which is that your arrows always point out of the object, never in. Cool? In the correct direction. All right? Now, we're also going to be interested in the velocity of the object, the motion of the object. So we draw a separate arrow for the velocity. And it's basically the same idea. The big thing is that when you draw your velocity vector, it doesn't touch the object. You just sort of draw it off to the side or below or somewhere near the object, but it doesn't physically touch it. Okay? And then again, the arrow points in the direction the object is moving. The larger the velocity, the longer the arrow. Label your velocity, v equals 8. And then if the object isn't moving, you just write v equals 0, so that you know, oh, the velocity is not, or the velocity is 0. Cool. All right, so let's do some examples. A very heavy shopping cart is rolling west toward Roy's new car at 6 meters a second. So Roy attempts to stop the cart by pushing it with a force of 20 newtons. Make a drawing. So there's two vectors given in this problem. There's a velocity vector and a force vector. So this is basically just showing you how to draw. So you draw the object, in this case a shopping cart. If you can't draw a shopping cart, then draw a box. Okay? All right, it's rolling west towards Roy's cart, 6 meters a second. So that's the velocity, right? So when you draw your velocity, just draw it somewhere near the object, being careful not to make it touching the object, because when it points out of the object, that implies that it's a force. All right? Technically, the arrow shows me what I'm trying to... The arrow shows me which direction it's going, but technically that also means my velocity should be negative, right? So put a negative there because you'll need that negative in your calculations. Okay? if you leave a negative off of a drawing, I will not take points off as long as you have the arrow there. But if you leave a negative out of a calculation, you'll lose points because then your answer will turn out wrong. So, make sense? All right, so the car's rolling that way. He's trying to stop it. Which way is he going to push, you guys? East, right? So, remember, your arrow should start inside the object that's being pushed and point out. I just remembered the seventh thing. Force of Roy equals 20 newtons. So that would be my free body diagram there, or my force drawing, I guess. It's not rocket science. The big thing, though, is force starts inside the object and points out. Sorry?
So the freestanding drawing should just kind of show what's going on.
Yeah. Eventually we'll get to solving stuff, but yeah, right now it's just, we're talking about drawing it. Okay, so notice, when I look at this drawing, I can tell that it's the shopping cart that's being pushed because the arrow comes out of the shopping cart. And I know what's pushing it because it says right here that it's the force of Roy. Okay? So every force is going to have two objects associated with it. The thing being pushed or pulled, and the thing doing the pushing or pulling. Okay? The thing being pushed or pulled is the thing you draw. The thing doing the pushing or pulling is labeled by how you label the force. Follow? Here was thing 7. I see people do this all the time. This is wrong. We'll go, oh, there's a shopping cart. It's moving this way at 6 meters a second. And there's a force from the cart. No. Because this drawing right here is implying that the cart is somehow pushing the cart, which doesn't happen. A thing can't push itself. That was thing number 7. A thing cannot push itself. Because look, it doesn't work, right? Like you can push yourself all day, you're not going anywhere. Okay, it's what's called an internal force. Okay, you can't, if you run out of gas, you can't sit inside the car and push the dashboard. It's not going to make the car go, right? You have to get outside the car and push it for that to work. Okay? So this is a big no-no. You will never have, whatever your object is, you'll never have a force with the same name as that object. Cool? And if there are two carts, then number them cart A and cart B. Number them A and B. Are we good? All right, very good. All right, Roy is driving to the Lady Gaga concert. He's very excited to see her. What? Yeah, that's what I said. So there's a cow on the road. Roy's going to pull the cow. There's not much point to this example, so here's our cow. Oh, I'm happier with this cow than the one I drew last hour, so. All right, so there's our cow, right? It's the udder. Yeah, I know female cows don't have horns. So, science. All right, the cow is standing in the road, so the velocity of the cow is 0. So just label v equals 0. I was literally just shouting into the microphone then. All right, and then Roy pulls the cow to the west. So label it. Force of Roy equals negative 50 newtons. Cool. So no big deal. All right, everybody good? I probably could have skipped that example. Okay. All right, now, new definition. Net force. Sometimes also known as total force. Depending on who your instructor is, you will see this presented both ways. So I'm going to present it both ways. All right? Sometimes it's called net force. The Greek letter sigma, you know how in math triangle means change in? Delta, right? Oh. I can feel the pain. All right. Yeah, so the triangle means change in, means subtract. The Greek letter sigma means total. It means add all these things together. Okay? So, very often the Greek letter sigma means net force, or the F obviously means force, so this is net force. And then sometimes it's just written this way, F total. Okay. So, either way, these both mean the same thing. Net force, total force. Net force, total force. Definition is the total of all the forces. So you're going to take all the forces that are on the object and add them up. Using what process that you just took a test on? Vector addition, right? Okay. That's all over the place, this chapter. All right. Now, this chapter is going to be split up into 2 chunks. All right, the first test will not have any crazy complicated vectors, but the second part will. So if you did not get an A on that last test, you need to find time to come see me and make sure that you understand whatever it was that you didn't understand the first time through, or you're going to struggle from here on out.
So tonight's homework won't have any of that.
I think there's one, but it's literally exactly the same as what we did on the last test. It's very straightforward, very, very straightforward. Okay, now, so your total force, your net force, is not drawn as its own force. All right, so jumping back to the cow example, what's the net force on my cow, you guys? Negative 50 newtons, right? That's it. There's only one force, so the total force is negative 50. So you just sort of write it off to the side, and you go, oh, the net force is negative 50 newtons. You do not draw it, because then it looks like there are two 50-newton forces pushing the cow. So the net force isn't sort of its own force. It's the total of all the forces that are there. So your drawing is going to list all the forces, and then just somewhere off to the side, you write down what the net force is. Cool? All right. Any problems about? So that's what this says. The total force is not sort of drawn as its own force, but it can be written near the object for reference. And I should have said, should be written near the object for reference. Cool? All right, we are almost done then. So I think the only thing we got left here is just some simple examples, all right, of just finding net force. But at this point, really, everything we're going to do is going to be horizontal forces. So you're literally just adding a positive, maybe two positives or a positive and a negative or whatever. All right. Okay, so this first example is silly. We get a large refrigerator sitting at rest in the center of a room. So here's the refrigerator. It's sitting at rest, which means the velocity is 0. In A, it says Roy pulls it to the right with 8 newtons. So pulls it to the right. So here's my force of Roy. It's 8 newtons. All right. What's different in part B, you guys? He pushes it. But the drawing is the same thing. All right. So that's the only point of these first two examples. Is I want you guys to understand. Whoa. I want you guys to understand that those are both literally the same thing as far as the drawing and calculations go. Even though one of them has a pull and one of them has a push, it doesn't matter. There's a force of magnitude 8 newtons forcing it to the right. Cool? Yeah, Christina. Yeah.
Oh, yeah.
Yeah, you'll see. All right, are we good? Yeah, I know. This is one of those things where I debated, like, we can kind of just mush this in and jump into the first law. And although it's super easy, it's super important. So these little things, if you don't get them, the rest of the chapter's a mess. So we're just spending a day to get going. All right. So sometimes you'll have more than one forces affecting an object. So this is more what the homework is like. All right. So it says Roy pushes a box. Oh, wait, let's see. A large box is sliding to the right across a frictionless floor at 5 meters a second. So label that. V equals 5 meters a second. Make a drawing and find the net force on the fridge. If A, Roy pushes it to the right, force of Roy equals 8 newtons. And Sally pulls it to the right with 12 newtons. What did I do with Sally's force? I made it a little longer because it's a little more force, right? Cool? All right, what's the net force going to be? 8 plus 12 is 20. Cool? All right. Ooh, really good question. Do you have to add the 5 as well? No, because it's not a force, it's a velocity. Apples and oranges, right? You can't add 5 apples plus 3 oranges. It doesn't make sense. You can't add newtons and meters per second. Really glad you asked that. Everybody good? All right. All right. Example B is the same thing, except now Roy and Sally are pushing and pulling to the left. So you go, all right, well, my box is sliding to the right at 5 meters a second. But now my force of Roy is negative 8 newtons. My force of Sally is negative 12 newtons. So now my net force is -8 plus -12, which gives -20 newtons. So we're totally going to have negative forces. Cool? Any problems? Easy peasy. All right. All right. So I think these are the last two I need to do, and then I think we're pretty much done. All right. So a large box is sliding to the left on a frictionless floor. So here's the floor. Here's the box. You don't technically have to draw the floor. I always do, just for reference. Let's see. It's sliding to the left. So V equals -4 meters a second. Roy pushes it to the right. Sally pulls it to the left. So find the net force. 9 plus 15 is 24, right? Yeah. This 15 newtons, well, I guess more to the point, the 9 newtons is working against the -15, right? So 9 of these cancel 9 of these. It leaves us with -6 newtons. That's why it's sort of net force, like net phase, right? Right? It's like what you gain minus the stupid taxes, right? Same idea here. Cool? All right. Now, tomorrow we're going to learn Newton's first law. Here's your entryway. Roy pushes to the left. Force of Roy equals 18 newtons. Sally, oh, that's wrong. That's not left. Sally pulls it to the right. So here's my force of Sally, and Roy pulls it to the left. All right, let's see, my velocity is still -4. All right, what's my net force going to be here, you guys? 0. All right, there is a whole law devoted to what happens when the net force is 0, and that is called Newton's first law. All right, I will tell you about it tomorrow. All I will tell you right now is this. It doesn't mean that the object is not moving necessarily. Sometimes it means the object is not moving, but not always. In fact, usually not. All right. I think that's that. Are there questions? All right. Margaret, a minute ago you asked if there were going to be any problems with vectors. There's one problem like this. This is literally like almost word for word one of the ones that was on that last homework assignment. So I'm not going to go through it, but you know, you're going to be given vectors at angles and you got to find the components and add them up. Cool? All right. I think that was it. Oh, you know, look, can I do one other real quick thing? Yeah. How about this? What if I told you this? Oh, that's not going to work at all. All right, so in other words, I told you guys, if you know all the forces, you can find the net force, right? Sometimes you need to subtract. All right, so here I gave you the net force. I'm telling you, oh, there's this mysterious box, and it has a net force of 27 newtons. And then it says, Roy is pushing it with 42 newtons. And it wants you to find the force of friction. So if Roy's pushing the box that way, he's trying to make it slide that way, presumably. So which way would friction be going? The other way, right? So this is asking how much friction does there have to be? Well, you just go, oh, well, let's see. Net force, by definition, is all my forces added up. It's the force of Roy plus, in this case, the force of friction, or missing force, right? And it's all linear, so I don't even need to worry about vector addition. I just got to watch my signs. So let's see. My net force was told to be 27 newtons. That's got to equal the force of Roy, 42 newtons, plus force of friction. And then what do? Subtract 42 and find out that your force of friction is 27 minus 42, which is what, -15? newtons. So there's your force of friction. Make sense? So there are a couple problems on the homework like that, where you know the net force and you get a method. Good?
Yeah.
All right. So if you did not get one, the homework is in the back. It's two-sided sheet. 3.1 is due tomorrow. 3.2 will be due the day after tomorrow.